Hello and welcome to Homework 2 Separations Part B. Just wrapped up video 1 and we are going to do video 2 now. As you can see here in Part B, I'll highlight it for everyone. We are going to use the Google JAX AI framework to calculate an NRT activity coefficients for multi-component mixtures in two ways. First, we're going to be using that JAX automatic differentiation. And then next we'll be doing direct calculations from the NRTL activity coefficient model. And then to use this, we're going to calculate 30-30-40 molar mixture of isopropanol water and toluene at 300 degrees Kelvin. So now that I have read to you all the equation, let's actually begin. So the first step is going to Colab. We're going to import our CHE library, so we're able to do all of this. Get rid of this, and then we also need to, like we said, we're doing isopropanol water and toluene. So let's get our chores done and let's get all of the information that we need to complete this process in here. It always takes about 15 seconds the first time you run this because it actually has to take the time to import this entire library. And we are good to go, so let's begin our video. So let's begin typing. We first need to create our NRTL values. So let's just name this NRTL parameters. And that is going to be Tij equals Aij plus Bij divided by T plus Cij times our natural log of temperature plus Dij times temperature. Now the next portion of this, we're going to be defining our NRTL Gx, which is a function of x and temperature. And now we are going to define things such as tau g, tau gx, and gx. And then we are going to be returning our JNP sum. So let's get started with that. So we have tau is going to be equal to essentially this equation right here, but we're going to be adding in our NRTL function. So we'll do p dot NRTL underscore a plus p dot NRTL underscore b divided by t. We're going to add n dot, so p dot NRTL underscore c. Here's the JNP dot log of our temperature plus p dot. Should just copy p dot NRTL so I don't have to keep doing this, but nonetheless, times t. Next we have our g value, which is going to be equal to JNP exp of negative p dot NRTL underscore alpha times tau. And like I said, we need tau g. We also need tau gx and gx. So those are the last two things we have to plug in. And for this, obviously, tau g is just going to be equal to tau times g. And then tau gx is going to be equal to the JNP summation. That is not correct, unfortunately. So we cannot use Gemini here. This is going to be ji, comma j 2I, and that will be tau g and x. I think that's typed right. And then we will use JNP dot again e in sum, and this one will be ki instead. We want k 2 G and X. Then finally, we also have to return our values, so we get a reward for all this work. And that's going to be J in sum X times tau G X divided by GX. Alright, so let's run this and see what happens. So we ran it and we did have one error. I had a syntax error up here. I think I used, I think I clicked K, or I don't know. I didn't use P dot, I used something else. But so we fixed that, and now we have 3 green checks and we're able to continue. Okay, so now we have 3 steps that we're going to complete. First, we have to define what jax.grad is equal to. And that is going to be equal to jax.grad. That is correct, but we also need our parameter 0 included. Then the second part of this, we have to put in the parameters and specifications that we were given here. So there's 30, 30, 40, and 300 Kelvin. To do that, we want to start creating an array. X equals np dot array. And here we need those parameters 0.3, 0.3, 0.4. We want to set our temperature equal to that 300 Kelvin. And then jnp.exp jax underscore grad. And we want this to be a function of x and temperature. So let's see what happens when we plot our array. We do have an A here. Tau gx not defined. Let's get rid of this. I don't think we're meant to have that. Tau gx not, oh, here we go. Gx, we want lowercase. Here we go. So we are given our array and we're able to actually analyze this. So now we have completed this first section. I'm just going to kind of summarize what we did here. So this gx, get rid of that. This gx grad here, this is actually the part that is most important. This is the automatic differentiation. So we can label this. This portion is what's going to be different from the next portion, because in the next section, we're just going to be using direct calculations instead of this differentiation to get this array. So we have successfully completed the first portion. Now let's go into the next and see how they differ. So now, as I mentioned, we already have all of these isopropanol, water, toluene. We already have the chores. So we're able to actually just use that stuff to move into the next portion. And we're actually going to just start with defining our NRTL. Now this first section is going to be the same. So we can just go up here and all the way until tau g. We can take this, simply copy paste, thanks to our good work that we previously completed. And we want you to go back there. And now, but here's where things differ a little bit, since we're doing direct calculations instead of that automatic differentiation. This next is going to be x tau g, and that is going to be equal to jnp dot in sum of this same value. So that is completed. And then next, this xg is going to be equal to exactly this. So really it's just a couple different variable identification, markers are going to vary. But then this whole new term, we are actually going to have a x tau g div x g. And that is going to be x tau g divided by xg. And then finally, we need to return all of this hard work. And to do this, we need jnp.exp. Now a lot of this is just going to be returning the values that we want, so we can create an array to see if there is any difference based on how you solve these. And we want j comma I HJ2I you also want X, we want G, we want actually G times tau minus X tau G X G. Did pi xg. Whole lot of syntax in this one. Let's see if we're able to run this without any errors. So good clean check marks across the board, and we can continue. So the final part is us getting this array of our NRTL values, x and t, and let's run it. Perfect. So now, to recap, this first process, we use this Jack's automatic differentiation of the excess Gibb energy equation of the NRT value. To do this, we put all these, we use tau g, tau g, tau g, x, and gx. And using this, we were able to create an array like this. And then using a different method, using this method here of direct calculation, we were able to go through, start out the same, but then we also needed an x tau g. We utilized the e in sum. We used xg, x tau g, div xg. We went through just a little bit of a different return value, but we arrived all at the same place. And it just goes to show you that sometimes in these situations, there's multiple ways to go about it. It's not always a right or wrong situation. It can just be what you prefer, which is more efficient, what you're more comfortable with. And so here we were able to prove that these two different methods arrive at the same value. So thank you.